Our next talk is going to be given by Yann Leray on encoding the cake and eating it too, controlling computation in type theory locally.
I'm going to talk about how you can control computation in type theory locally, and this is joint work with Théo Winterhalter. So first, what I mean by computation is pretty much definitional equality, which is what allows you to, when you have a goal as simple as 2 + 3 = 5, to solve it without doing any work. You just tell the proof assistant kernel to deal with it by itself, and this is the fragment of equality that is decided by the kernel, as Stephanie already explained. And so it works for simple goals, but you can also make it so that a wider array of problems can be encoded and solved by the compiler, the kernel itself, using reflection solver. So you can have you can solve ring theory, and also, as Damien explained in the keynote on Wednesday, this can also be applied for linear algebras and monoidal category adapters. So quite a wide array of problems that can be solved. On the other hand, you can also, if not every type theory has the same definitional equality, some have more than others. An example is observational equality, in which if you have an equality on pairs, this is equivalent and convertible to having a pair of equalities on each of the fields. And also, proof irrelevance is another big example in which any two elements of a type, when this type is a proposition, are considered to be convertible. So what should be understood in this is that more computation, more definitional equalities is better for the user. It solves more problems, and it makes it possible to express more things. So my question is, how do you extend definitional equality in type theories? The first, most simple answer is to use a rule called equality reflection, in which you make it possible, as soon as you have any propositional equality, which is the one you can manipulate as a user, to be able to reflect it in the kernel, in the definitional equality, and add it to the theory. So this sounds wonderful, any equality in my theory, but there are quite a few issues with that. First thing is that this is conservative, sure, but over ITT plus UIP and function extensionality. So ITT is pretty much the set of rules that is accepted, but UIP and function extensionality are things that you may not want to assume. And what I want to say, it's not always available, and you also don't want to assume it every time. So this is a bit of an issue. You may try to be smart and do a translation from this to ITT. There are works to do that, to try to see whether the axioms that you used were really needed, but this translation is also terribly inefficient. So this is a bit of a problem. And my biggest issue with this is that this makes type checking undecidable. So sure, your definitional equality is large and has everything you want, but if the kernel doesn't compute anything, is it still really computation? I don't think so. So that's why I'm going to leave this away and explain another way to do extensions, which is going to be more reasonable, rewrite rules. So this is a small example for Booleans and how you can implement them using rewrite rules. So first, you're going to postulate a few symbols. So Booleans, its constructors, its eliminator, if then else. And once you have postulated those symbols, you can define the rewrite rules, how the, in this case, eliminator is going to compute. So if then else, if true, then return the first argument. If false, then return the second argument. And once you have expressed all the theory, you can do definitions using that, for instance, Boolean AND. And when you ask the kernel, your proof assistant, to evaluate this function, this will reduce and we'll get false and true is false. So this is a simple example. Booleans is something that you can usually already define or already have in your proof assistant, so it's not exactly interesting. But rewrite rules also allow you to do more different things. Here, you can define a symbol raise for an exception and hijack all the eliminators on all the previous things that are already defined in your type theory. Here, the eliminator on Boolean, when it computes on raise, maybe it will just return the exception itself. And this means that you can override how these symbols and symbols from your theory compute. So rewrite rules sound nice, but they are still quite dangerous. Here is about pretty much a copy of the previous example, but with one slight difference. Will you be able to spot it? I think not. And most importantly, neither does the proof assistant. So here the small difference is that I changed what if then else applied on false returns, make it return the first argument instead of the second one. This is quite subtle. It's difficult to see as a person, and the proof assistant will just accept it without any condition because it's a valid rule. So it's dangerous. Another big danger is that when you postulate a symbol like an exception, it makes the theory immediately inconsistent. So yeah, sure, you can define a definition to get the nth element of a list and have it be total, raising an exception when the list is empty or not large enough. But then, if later in your file you prove a theorem which is totally unrelated, you have a nice proof, but how do you make sure that this proof didn't use either raise or the rewrite rules associated with it? It's quite difficult to track and maybe difficult in practice, so it's something that we may want to avoid. So overall, the danger of rules and global rules as they are presented here, they have dangers quite similar to axioms, but even worse because more difficult to track. Axioms have been better studied. We know how to do this, and we have a quite good solution to mitigate these problems, which is modularity, making sure that axioms don't leak to wrap them in a box. And that's pretty much the solution that I'm going to present for rewrite rules. So our solution is called LRTT, Local Rewriting Type Theory. And for bools, what we are going to do is put all of these symbols and rules that we postulated, put them inside of an interface, such that definitions which want to use the symbols and the rules are going to explicitly take as an argument which is going to be at a high level, but argument still, the Boolean interface, and then, for instance here, define the Boolean negation using the eliminators and symbols already defined. And what's possible with an interface is to also have implementations, to have an implementation associated with an interface. Here, as an example, I gave the definition of Boolean that C uses using natural numbers. So you can define Booleans to be the natural numbers, false is 0, true is 1. You can define the eliminator for Booleans using the eliminator for natural numbers. And what you should see is that there is absolutely no field or no information to make sure that the rules are satisfied. This is going to be verified by the type checker, by your proof assistant directly. The equations need to be verified on the nose. They need to be definitional equalities. Otherwise, this won't work. But this is done automatically, and then you can use use a new definition to reuse the neg-b, which took a bool and instantiated with the natural numbers instead. So this can be used in a few different ways for your theories. First big thing is that you can use it to hide implementation details. Here we have a small example shift, which is supposed to take a list of natural numbers and bump each element in the list by 1. So you write the rules that it's supposed to have. On the empty list, it's going to return the empty list. On cons, it's going to return the cons shifted by 1. It's a simple function. It has a simple implementation that you already thought about, which is just using list.map and applying successor at every time. But what this allows you to do is that as a user, when you depend on the interface shift, you're never going to see the implementation. You're never going to see list.map in your proofs. When you do computation, when you try to change the type because you're doing a proof, this is nice not to be able to see stuff that you were not supposed to see, and it's just going to pollute your proofs. So this is a simple example, but more generally, you use this to do control unfolding, to hide auto-generated subterms, which is quite a big issue in Rock's plugin equations, which sure is able to deal with terms with difficult and dependent types. When it has tactics to deal with it, and when you use the tactics, it works fine. But as soon as you stray away from the good path, you bump into the auto-generated terms it defines, which are huge and unwieldy. So it's nice to be able to hide them. And also, you can do strictifications, which is an encoding, in which you take a structure which has, how do you say? You have a structure, you encode a structure with difficult definitional equalities using some encoding which is going to be ugly and unwieldy to define, and you can still wrap it and only postulate the definitional equalities that you want to see, not have it unfold to its definition. Similarly, you can encode features like inductives. W types are known to be universal types for universal inductive type, and this means that you can only postulate W in your kernel, in your proof assistant, and then have and postulate every inductive as an implementation using W, but wrapped so that you never want to, so you never see W, because when you deal with natural numbers or Booleans, you don't want to have to deal with W directly. And we can try to combine both of these approaches to have an unsafe but working encoding for quotient types in any, in this type theory. So let me go over the theory. Our main judgment for typing is going to be this quite large judgment with quite a few parameters. So the rightmost part, gamma, says that T has type T, stands for the usual MLTT judgment, but it's going to have two more parameters for more, because more things are going to be involved in our typing rules. So sigma is our environment, which is just a set of the definitions you did, definitions which are going to be able to depend, to take as argument interfaces, and interfaces are going to be stored in this psi parameter. And here are a representative subset of the rules in which are added in LRTT. So I'm going to go over them slowly, don't worry. So as I said, definitions are going to take as arguments a special argument outside of the rest of the term theory, an interface. They have a type and they're defined as with their definition, and you just want this term to have the good type, the right type in the right environment. Here, when we postulate a rewrite rule, the rule lives in some context for all the pattern variables that are going to appear inside of it, and we only need, for the theory, that both sides of the equality have the same type and live in the right context. So it's quite a small requirement for rules, and it's going to bite us a bit later. Then here is the definition unfolding. So what we are going to do is quite simple. If f is defined as t, and we use f with an instantiation, we are going to give the implementation we want for the interface that f depends on. Well, it's just a matter of using t, doing an instantiation, it's just the equivalent of substitution for this new kind of arguments, but it works the same, just not the same variables. And these two are going to be convertible. And finally, rules is pretty much the same, except that this time these are regular substitution because they were regular context, and you get this conversion. So LRTT is a quite nice theory, and it has all the usual properties of the type theory. This is proved in a ROC development, which is fully available. It's in the artifact. So we proved the usual properties, weakening, substitution, instantiation. So this is all fine. But the most important one I'm going to highlight now is compatible with definition inlining, which means that if we define these brackets to be a homomorphism, so we are just going to take the term, go into every subterm, and every time we see a definition, we're going to replace the definition with a defined symbol, we're going to replace with the definition, and recursively. Note that this is still well-founded because T lives in a smaller environment than F, so it's all fine, don't worry. And the result is that the typing derivation we had at first is stable under this inlining, and this is quite good, but what it allows us to do is that when we have a type which is closed, doesn't depend on any interface, then it's typed in MLTT. LRTT, when we don't have access to interfaces, has the same typing rules. So this was supposed to be empty. This means that when we have a type T, which, T may depend on definitions, but here A doesn't depend on any definition. T depends on definitions, but we can inline their definitions and obtain a term which lives in an empty environment. A has had the same treatment, but since it didn't use any defined variable, it stays the same. And this means that LRTT is conservative over MLTT. Okay. I highlighted the rule for using rewrite rules. In the theory, this was underacted. This doesn't make for a decidable type theory. So for now, it's not better than extensional type theory. But we have a way to make it work, which is just to limit ourselves to rewrite rules. That's why I started with them. But this means that the restrictions of rewrite rules are still going to apply. The rewrite rules only work in a type theory when they don't break up the confluence of the whole theory. They also need to preserve typing so that the conversion algorithm stays correct. And another problem that rewrite rules might introduce is they might not be terminating. If they are not terminating, the conversion algorithm might just stop being complete. But at the same time, if the proof goes through and the algorithm terminates, then the proof is still valid. So it's still it's not as important as the rest. In ROC, there is already a notion of implementations and interfaces, modules, and actually this is quite a nice, good place to integrate our rewrite rules, our local rewrite rules, and that's what we did. So here, again, the same example for Booleans, but here in the ROC proof assistant, or in a prototype based on the ROC proof assistant. So instead of the keyword interface, you're using the already existing notion of module types. The syntax is a bit different, but the meaning is the same. And the implementation, you just use modules, or here functors, because it's going to depend on an argument. But otherwise, this just works. And the plan is that, so for now, this is a prototype, and also soon to be a pull request. We plan to have this integrated in ROC 9.3. Very quickly, I told you that we could implement quotient types in ROC. So this is a variant of Lie using originally private inductives. But here, we can be even more simple and just, so this is quickly I hope, the interface you expect of quotient types, where T is the type of quotient. And what we could do, we can do is just have the type of quotient be the carrier type itself, have all of the relevant functions be pretty much definitional. You add an axiom, which is absolutely unsound when you're in the module, which says that the constructor for the quotient, which is just identity again, is injective, where there is no reason for it to be. But since here you made sure that you sealed this module with the proper interface, and as soon as you leave this, it should be right, and you should just have a quotient. So, to conclude, LRTT is a framework for local extensions to a computation for a type theory. It allows you to hide implementation details, encode features, and contain extensions like quotient types. It's conservative over MLTT, and it's available as a prototype, and hopefully it can be integrated in ROC 9.3. Quite some perspectives, this depends on the existing implementation for rewrite rules with its existing limitations, and as a whole, we can just hope to improve these limitations. It's going to help in a lot of instances. And instances and in implementations, rewrite rules were implemented with a test for definitional equality, which makes it simple and reasonable as a prototype, but it would be better if we allowed propositional instances. This is getting very close to ETT territory, so we need to be very sure of what we are doing, but still a perspective that is quite interesting. And I guess I should find a postdoc soon. Thank you.
Any questions?
Hey, thanks for the great talk. Is it microphone? That okay. You said that you were checking termination and also confluence. Okay, so it sometimes works. So you said when checking termination and on the microphone. So okay, now it works again. Okay, great. Right. So you were checking termination confluence, and I was wondering.
I was checking what? Sorry.
You were checking termination and confluence, or you wanted to check for your rewrite rule set, I think you mentioned that. And I was wondering whether you considered using Knut-Bendix completion to make it terminating and confluent.
I'm sorry, the mic doesn't translate your speech
I can
that well.
That's unfortunate.
Did you consider using Knut-Bendix completion to turn your rewrite system into a confluent and terminating one?
Especially for this work, we didn't focus very much on improving the situation for rewrite rules, because this is orthogonal work I'm also pursuing. In general, for rewrite rules in ROC, we have a confluence check called the triangle criterion, which is probably weaker than Knut-Bendix completion. Not probably, it is definitely weaker, but at least it's easy to formalize. It was easy to formalize and make sure it works. So this is a definite a way in which we could improve, try to see and implement it and make sure that it still works in the theory, but definitely future work.
Thanks.
Thank you. I use auto-rewrite a lot for proving equalities by normalization.
Yeah.
Can I do, using your technology, everything that I was doing using auto-rewrite?
Probably not. The thing is that equalities, propositional equalities, and the thing you can give to auto-rewrite as a rewriting tool are more expressive than what rewrite rules allow you to do, because rewrite rules need very syntactic heavy checks and have limitations to make sure that the typing and the confluence, especially for the typing, to make sure that it's still preserved. Also, I don't think auto-rewrite has any confluence check. It can just go for a very long time. It's probably just a timeout, not a proper confluence. So, yeah. It's more limited, but probably for good reasons.
Related to this decidability of type checking, maybe this is too naive, but if you have an implementer of your module, does that prove these properties?
No.
Okay.
First, the confluence has nothing to do with the implementation, because when you give the implementation, you say that there is a definitional equality, but you between having a definitional equality and having a directed thing, you completely lose everything. Type preservation is way more subtle. In type theories like Agda's, generally when you don't have cumulativity, it's quite difficult to break type preservation. So even just postulating it usually is enough. When you have cumulativity, which is the case in ROC, and that's the main goal for me, it's way easier to break stuff. So you need some check, and I'm pretty sure definition, an implementation isn't enough to make sure that it works. So yeah. It's really tricky, and these side conditions, they need to be checked anyways.
You mentioned equations. It would be very nice to have like better support there, but like how hard do you think it is? And in particular, like I feel like most of equations do not hold definitionally. Like as soon as things start to be a bit more hairy, you do have like inversions all over the place and so on. Like, do you think it is reasonable to hope that we can have something like basically like ACTA, where you actually like get the right equations that you want and everything works out? Or is it like kind of a too wild a dream?
I guess there are two dimensions that equations allow you to do, either structural and using the general fixed points made available by ROC. And in this case, what you see by equations and what you get is the same. It's just that there's a huge encoding behind everything. And this means that since what you see is what you get, you can write exactly that and have exactly that as rewrite rules. As soon as you have accessibility involved, then a priori the rule that you're going to get is going to mention accessibility as well, which is not something that you actually want, but probably still as good as can be. I'm not sure exactly how it would look like.
Okay, but so for the fragment without termination proof, you think it is reasonable to hope that we can get something good then?
I mean, you already have an implementation for the thing, so it's just a matter of wrapping everything using the rewrite rules that are already expressed in equations, rewriting lemmas that are used by its tactic. So I don't think there should be any issue there.
Thanks.
Maybe I'm too hopeful.
In the interest of time, we'll take the rest of the questions offline. But I'm hopeful as well, Yann. Thank you.